to this session. We have 6 papers in this session, and we have 1 hour. So I suggest the following procedure. I would like to follow the default order that is announced in the program, and would like to spend at most 8 minutes per paper, so that at the very end, we have some time left to ask questions to any paper in any order. In the beginning, we start each paper with 2 minutes that is allowed to the presenter to recall the topic and the result. And yeah, we will start with Libor Barto, who is also the video presenter of the first paper about sensitive instances of constraint satisfaction problems.
All right, hello, can you see the screen?
Yes.
Okay, no, I cannot. Yeah, so this work is about constraint satisfaction problems with fixed templates. So the input is a set of local constraints where each constraint relation comes from a specified set. And the task is to determine whether all the constraints can be satisfied. And a standard preprocessing procedure is the k+1 consistency algorithm, where we derive strongest possible constraints on k variables by looking at k+1 variables at a time. And the paper is about how good this algorithm is. So here are like 3 levels we can have. I call the algorithm so-so if it actually can detect whether the solution exists. So then k+1 consistency procedure can be used as a decision procedure for the CSP. I call this algorithm great if not only it can detect solutions, but if you perform this procedure, any reasonable assignment to any reasonable partial assignment can be extended to a solution. And what we study in the paper is somewhere in the middle, which I call good. And this means that every partial solution on exactly k variables extends to a solution. That exactly means that if you sharpen some constraint, we invalidate some solution. So this is why we call it sensitivity. It's an instance of CSP. So that every tuple in every relation plays some role in some solution. So the results, or part of the results, are here. So these are some old and some new results. If we fix such a structure and consider the CSP over such structure, now I'm not going to explain this Hess compatible whatever. You can understand it as if. So let's read the second item, the great item first. You can read it as follows. So if the template is symmetric enough, then the algorithm performs great. So every partial solution can be extended to a solution. This notion of symmetry is actually not random. In this case, it precisely characterizes those templates which have this property. Okay. So this is the great performance. The so-so, if the template has like some weaker or way weaker level of symmetry, then one can use it to detect whether the instance is solvable. Again, this result has exact converse, but with some other even weaker level of symmetry. And our main result implies that if the template is somehow symmetric, somewhere in the middle of these two, then the algorithm is good. So any instance after performing the consistency checking is sensitive. So every tuple plays a role. We do not have an exact converse in this setting. We do have some converse in a bit different setting, algebraic one, which I'm not going to talk about. And let me also mention here that it works for infinite domains as well. So this is not restricted to to finite domain CSPs. So here are just a few examples. If you don't know this topic, this may shed some light on it. So solving systems of linear equation is a problem that can be phrased as a CSP, and the consistency algorithm is useless. So it's not even so-so for any K. Hornsat is an example which is so-so, but not anymore good. So it's not good, not great. Two-sat is the great problem. And I cooked up some example which is good but not great. So somewhere in the middle. This is some fragment of linear programming where one variable corresponds to two binary values, and you can ask these three constraints. So the interesting one is that the sum of the four values is at least 2. So this is an example where the level of consistency is exactly achieved. Right.
Thank you very much. So I propose the following procedure. I would like to start with questions from the people who are willing to share the screen on Zoom. So if any of the followers in Zoom has some question, he can just speak up with the mic.
Yeah, hello. So I posed a question also on Slack. So I think on the last slide, you mentioned that you are also considering generalizations to ω-categorical structures. What exactly, can you go into details here?
All right, so this is the last item. So what we can prove is that if we have this nu, let's say k plus 2, and we enforce k plus 1 consistency, the instance will be sensitive, assuming we have local idempotent near unanimity operations of arithmetic k plus 2. So we need, it's enough to be local, which is fine for infinite domains, but we need to be idempotent. And what would be nicer to have, and which we don't have yet, is the same conclusion, but just having oligopotent quasi-near-unanimity operations. So those ones which are not necessarily idempotent, because this condition is exactly exactly characterizes greatness in some restricted classes of CSPs. So we have a problem with idempotency. That's it, and that's because you know the technicalities. It's because we don't have loop lemma for like non-idempotent things, and actually loop lemma doesn't work. It's probably incorrect. So it would require completely different strategies somehow to prove this.
Thanks. Thank you. Are there other questions? I actually have a follow-up question to this one. So did you look into some examples, like for instance, OR horn? Or is again an infinite example? It seems to me that it is too good in your sense. K equals 2, but for higher K, I'm not sure if I look at this. Do you know this?
Well, we haven't looked at concrete examples at all. So thanks for suggestion. You said OR horn.
OR horn, yeah.
Oh, okay. I'll look it up.
Okay.
I might perhaps have time for a quick question.
That's Victor. Hello.
Hey. Just a question in a slightly different direction is perhaps one can think of two parameters, the K of the consistency and then the J of the, so let's call it J of the sensitivity. And can you consider like J's, have you considered J's that are smaller than K? This goes to, I mean, perhaps with weaker conditions than a nu, like for instance, for some large enough K consistency, you can guarantee that every one projection extends to a solution. Of course, if you have large K enough, that will be true, but maybe you can find what is like the right value of K for this. Did you look, do you think that is interesting?
Well, yeah, it's an interesting question. I cannot give you an answer. There is like, for NU, for example, if you perform 2-3 consistency, then every point, every feasible point will extend to a solution. But I cannot. Yeah, we don't have any exact characterization, and it's an interesting question. Yeah. So, for example, what you ask exactly, whether like any feasible point, feasible value for one variable extends, a natural question, and we don't know. Yeah.
Thank you.
So I think, as promised, let's proceed with the next paper so that every paper is treated fairly. The next paper is Hruschowski's encoding and ω-categorical CSP monsters. And I heard that Michael Kompatscher will give the recap. So please try to stay with 2 minutes so that we have a lot of time for questions in the remaining 6 minutes.
Okay, I try to. Sorry, I have some small technical problems in sharing the screen.
Yeah, maybe I didn't unshare the screen and I don't know how to do it. So.
No, I unshared the screen. You should be able to share by pressing the green share screen button.
Yes.
This looks good.
Yeah, so thank you very much. So our paper is about infinite domain constraint satisfaction problems. And there somehow the big tractability conjecture is that when we start with a structure, possibly a countable domain structure that's a reduct of a finitely bounded homogeneous structure, then either the polymorphism clone of this structure satisfies locally non-trivial identities of height 1, so identities that cannot be satisfied by projections, and then the CSP is in polynomial time, can be solved in polynomial time. Otherwise, it's NP complete. So like having no such height 1 identities, that's the only source of NP hardness. That's the conjecture here. And this generalizes like also the tractability conjecture or the dichotomy for finite domain CSPs. And now our paper is about what happens when you leave the domain of this conjecture. So we were looking at ω-categorical structures. And that makes sense because ω-categorical structures, they form a bigger category for which the complexity of the CSP is also determined by the polymorphism clone. So by all the operations preserving the structure. And now we used a model theoretical technique, which is called Hruschowski's encoding, and studied the properties of this encoding. And it takes as an input possibly an infinite structure in possibly infinite language. And you construct a finite language structure that somehow contains all the information of the original structure and preserves many nice properties of it, like also ω-categoricity and properties of the polymorphisms. And we use those Hruschowski encodings to construct ω-categorical structures that have pathological properties. So we were just starting with with ω-categorical structures that are quite trivial in a model theoretical sense. So all the relations are empty, basically, but there is a lot of complexity in there just in the signature of the structure. And we use those to construct now the encodings of those structures. They will be algebraically well behaved, but have weird behaviors with respect to complexity. And you can also use Hruschowski's encoding to construct CSPs that are weird in the algebraic way, but I will show it to you on the next slide in more details. So the first theorem I already mentioned, you can construct structures that have that are algebraically well behaved in the sense that they are satisfying non-trivial height 1 identities, so even on a global level, and that have basically arbitrary complexity. So we can find CSPs then that are co-NP to the C complete. So for arbitrary complexity classes C, such that such co-NP to the C complete problems exist. we can also find CSPs that are co-NP intermediate. Suppose that P is not equal to co-NP, and undecidable problems. Furthermore, we could show using also those Hrushovski encodings that whenever you have a complexity class that contains AC0, then the class of ω-categorical structures that have CSPs with this complexity, this cannot be described by identities. So no countable sets of identities, even if you leave the additional restriction of height 1, can describe this class. And the last thing was that we took an already known example, so of Manuel, Michael, Jakub, and Ross Willard, that you have an ω-categorical structure such that the polymorphisms satisfy non-trivial height 1 identities locally, but not globally. And using the Hrushovski encoding, we could also find a finite language such counterexample. Yeah, so this sort of shows that the conjecture from the previous page, that here it's not really reasonable to try to expand the range of this conjecture to broader classes of ω-categorical structures.
Yeah, thank you very much. Are there questions? I saw that your video has quite a number of views. Yeah, it's very well watched. You can see this in YouTube, how many views. And
yeah, but here the full credit goes to Michael, who is also here, and Julius.
Yeah, are there questions first from the Zoom people who can show their...
Can I have a question? So my question probably is more to the other Michal, because you partially answered it. So in the video, Michal, somewhere in the middle, he mentioned, and you mentioned it again, that polymorphisms of ω-categorical structures encode the complexity of its CSP, right? But he concluded with saying that there is no hope that we can use polymorphisms to get an overview of possible complexities. So in which sense does these two statements don't contradict each other?
So I would say that there he referred to identities of polymorphisms, but yeah, maybe the other Michael wants to reply to this.
Can you hear me?
Yes.
Okay. Yeah, I think your answer was that's the right answer. So probably it's the, I mean, we see that nothing can be described by identities within the whole class of ω-categorical structures. Also, it shows like there's a general problem with the class of ω-categorical structure, namely that you can encode any infinite signature structure into a finite signature structure while preserving the most important algebraic properties, symmetry properties, and so on. So that and really the structures we encode, they only have empty relations. I mean, to prove those, like the first two theorems, yeah? They just have empty relations. So they are really stupid structures, but just from the fact that they have a horribly named infinite language, they get these complicated complexities. And on the other hand, mathematically, they're like void. Yeah, up to the overhead of the encoding, they're void. So I find it very difficult to imagine a theory that connects within this whole class of ω-categorical structures mathematical properties actually to in a general way to complexity. This seems. I mean, I know I formally contradict myself, as you said.
Yeah,
but it just seems too the things that can happen, like the mathematical properties and the complexity, can diverge so much that it seems to me unreasonable to expect a good general theory. I mean, I cannot. It's not a formal statement because formally it's false, right? I mean, we know the complexity is encoded by polymorphisms, but giving a general like theory that would say which ones are tractable, which ones are not, seems unrealistic to me.
So maybe let me rephrase a bit of that. I think I understand how it cannot be characterized algebraically, but what is the formal statement that says that the polymorphisms are determined by, the complexity is determined by polymorphisms?
The former statement is that if you have two ω-categorical structures and they have the same polymorphism clone or the same polymorphism clone up to isomorphism, then they have, the CSP has the same complexity.
Topological isomorphism.
Yeah, so I mean topological, and I don't. So it is indeed. I mean that's a formal statement. It is, the complexity is indeed encoded by the polymorphisms, but theory which would say which polymorphism clones are good and which ones are bad seems unrealistic. I mean this. Yeah. So here Michael has shown you the theorems, but actually the proofs are worse than the theorems in the sense that he doesn't say that, he said it, he doesn't state on the slide, that the structures we encode, they just have empty relations. I mean, it's so. And
yeah, okay. Now I understand. Thanks.
So please, everybody who wants to continue to discuss this paper, stay online, because at the very end, we can come back to each paper. But now, at the moment, I want to proceed with another, at most 2 minutes presentation of our third paper. It's called The Power of Ordering in Linear Arithmetic Theories. And yeah, where do I have to? Yeah, Christoph is already here. Very good.
Yeah. So can you see my screen?
Yes.
Okay, good. Okay, yeah, so this is joint work with Dimitri Chistikov from Warwick, and it stays in logic, but it's not about CSPs. So in our paper, we study the complexity of the weak definability problem. So this is a problem that was first looked at by Geoffroy and Fingari roughly 10 years ago. And what we're having is, I mean, when we're looking at linear arithmetic theories, so which are theories, well, of linear arithmetic, where we have a domain, either the rationals or the integers, together with constants 0 and 1, and addition and order. We want to know if we're given a set that is definable in this logical theory, whether it's also definable in its weak counterpart. Okay, and by weak, I mean that the order relation is dropped, and instead we just have the equality relation. And we can look at this problem, well, over the rationals and over the integers. So Geoffroy and Fingari looked at this problem over the integers and showed that the problem is decidable, and they gave a non-elementary time algorithm for this problem. Now, so here are two examples of this weak definability problem, just to give you an idea, basically. So if we look at this formula phi here, it says that x is less or equal to -1, or it's x is greater or equal to 1. And then we can interpret x in the integers or in the rationals. And when we interpret x over the integers, then the set that is defined by this formula is weakly z definable by just saying, well, x must not be 0. Okay, so we're not using an order here. However, this set is not definable, it's not weakly Q definable. So basically, because we would need to cut out an infinite number of points between -1 and 1. And this is something we can't do. We can only cut out finite number of points if we don't have order relation available. And so this means that weak set definability doesn't imply weak Q definability, and the converse also holds. So if we are looking at this formula here, which is maybe a little bit more complicated, but all it says is that all numbers below 0 are multiple of 2, and all numbers above 0 are multiple of 3. Yeah. Then over Q, this is just the whole line of of rational numbers, but we can't. But it follows also from our paper basically that this set is not weakly Z definable. And so the main results that we have is that what we show is that the weak Q definability problem is co-NP complete, assuming that the input is a quantifier-free formula. And the second result is to show that weak Z definability is decidable in elementary time. And the problem is pi to p hard for existential formulas, even in a fixed dimension. And so this improves this non-elementary time algorithm. A nice side result that we obtain is the following. In order to show this pi to p lower bound for the weak Z definability problem, we show that the universality problem for ultimately periodic sets given in generator representation is pi to p complete. Ultimately periodic sets should be, I hope most of you will know it. I mean, it's a set of natural numbers that after a certain threshold become periodic. And given in generator representation means that we're giving a finite union of generators that describe this set. Okay, and so this problem was known to be in pi to p, and we established a pi to p lower bound also in our paper. Okay, so that's it from my side, and now I'll be happy to hear your questions.
Thank you very much. Are there questions?
Yeah, I have a question, Manuel. So, Christoph, I wonder whether you could say something about the complexity of Presburger versus weak Presburger, this open question, and what you conjecture might be the answer to it.
Yeah. So you asked this in Slack. I think I saw. Yeah. So I mean, I think what we get from this work is that sort of in the kind of sets they define, they behave very much like the rational numbers, like the rationals roughly. I mean, they are different, but they are still. It seems like they are more like the rationals than Presburger with an order relation. So my conjecture would be that it has the same complexity as over the rationals, basically. So it would be the complexity would be lower than for full Presburger arithmetic with the order relation. So that's my conjecture. So we've been working a little bit on this. Also, let's say not like we haven't really pushed it. Yeah. So the lower bound basically, so I had a master students who showed last year that the lower bound over the rationals is the same as in the order, as when the order relation is present, basically. Yeah. So this will immediately carry over to the integer case, and I guess the upper bound will also be possible to get the upper bound lower by 1 exponential compared to Presburger arithmetic.
I have a question, I think, related to this. Is this the same question as the question in your video? In your video, you asked about the complexity of weak linear integer arithmetic.
Yeah.
So this is p-space complete?
No. I mean, at the moment, the best upper bound is the bound from Presburger arithmetic. And there is an SDA, I mean, space-time alternation lower bound that is with exponential time and the linear number of alternations. So this is basically above p-space.
So you do have this lower bound.
Yeah, and there is also a lower bound. But as I said, the upper bound for Z is only the upper bound that comes from Presburger arithmetic. Sorry, did I confuse you?
So you, for this problem that you mentioned on the last slide of your video, you do have a lower bound.
We do have a lower bound, yeah, but we don't have a matching upper bound.
I see.
So by the way, I mean, this weak linear integer arithmetic is actually the Presburger arithmetic. Presburger originally studied in his article. He only said you can extend his quantifier elimination method also to work with the order ring relation.
Thank you. Are there more questions? One quick question is still possible. We can come back at the very end.
Yeah. So sorry, maybe a very naive question. What do you mean by elementary time?
I mean, well, exponential, but the exponent is fixed basically. Yeah. I mean, we at the moment we are kind of writing up a full version of the paper, so I can't tell you exactly. I think it's 4x. We think it's something like 4x time, but there are a couple of things we need to check. I mean, it's clear from the proof that it's elementary, but 4x, 5x, something like that. Yeah.
Okay, well then, the next paper in the schedule is Higher Order Cryptography, and it will be presented, I think, by Udo.
Yes.
Yes, very good.
Just 1 second. Okay, can you see?
Yes.
Wonderful. So, yes, so we are interested in looking at what happens when cryptographic primitives like hashing, authentication, or encryption are applied to code rather than to data. In this case, code is interpreted as a binary string anyway. Cryptographic primitives typically remain always there as functions or algorithms working on binary strings, even when they are applied to programs, to code. This means that whenever you apply the same cryptographic primitives, like, for example, authentication, to two programs which are just slightly different and equivalent, namely, they compute the same function, they have exactly the same behavior, you expect, for very good reasons, that the outputs are two different strings. They are two completely different strings. Think about hashing, but authentication is exactly the same. So, we may wonder what happens if you look at cryptographic primitives which are equivalence preserving, namely that they behave on programs respecting under the underlying equivalence. So this would amount to turn the type of the authentication algorithm we saw from a first order one to an higher order one. So this way, the authentication algorithm would look at the argument code as a function and not just as the underlying binary strings. And the results we get are threefold. First of all, we introduce a computational model based on game semantics in which higher order programs are interpreted as strategies, and this way accounting for their complexity, which is itself non-trivial. And the result here is that polytime strategies compose even if they can interpret types of arbitrary rank. And then we have two actual results about the cryptography you can define this way. First of all, we show that functional authentication is very hard to get if the authenticated function takes an input a string of linear length in the so-called security parameter, because this way collisions can be found in polynomial time, and since collisions can be found in polynomial time, well, you cannot hope to get any form of authentication, at least going through such a function. But if the authenticated function takes an input strings of logarithmic length, then you can get, and this is the third result, a second order pseudo-random functions, provided standard cryptographic assumptions hold, in particular provided one-way functions exist. So thank you very much, and I will be happy to answer your question.
Thank you very much. I know that we have some question already in Slack, but again, I would like to give preference to people who want to speak up in Zoom.
Yep.
Is there? I would like to ask the moderator to pass on some question from Slack.
Yeah.
I have as well. Yeah, from Slack. May I read out? In your video, you mainly talk about RNGs. I'm wondering what a second order encryption function would look like. It encrypts functions, but to what? Bit strings or functions?
Yes.
The key, a bit string or a function?
Yeah, thank you very much for the question. Indeed, second order encryption is not really what we have looked at in the paper, but this is work in progress and we are looking at it. It looks like the most natural form of second-order encryption is one in which the input function is indeed a function and the output is itself a function. So you encrypt functions as functions. And it seems that if you do so, second-order encryption is indeed feasible. But yet, this is a work in progress. We still haven't finished and finalized all the proofs.
Thank you. Let me take this occasion to inform everybody there is in Slack the option to continue discussion also after now our session. There are lots of questions already in there and discussed and answered. So please have a look in Slack. Yeah, this is important. Is there, I think there's time for another question, either from Zoom people or from the moderator. I read it out. Polytime strategies can only have interactions whose length is bounded by a polynomial in the security parameter. This seems reasonable and in keeping with standard crypto work, but is it restrictive in a higher order setting? Do you know of any crypto primitive that might require interactions that aren't polynomially bounded?
Yeah, this is like a very natural question. Actually, we introduced this restriction for two reasons. The first one is that most of the cryptographic protocols and primitives are indeed such that the length of the interaction is polynomially bounded. And this holds even in those cases in which the actual complexity of parts of the protocols is not polytime. So even if the complexity of the internal complexity of the parties, and this happens sometimes, is not polytime, the length of the interaction is typically kept to be polynomially bounded. The second reason is that proceeding this way, the first result I mentioned, so the one about game semantics, number one, that polytime strategies compose is, it just works. It just can be proved. If you do not have such a bound on the length of the interaction, it's very hard to prove polytime strategy to compose because you don't know how many turns in the actual strategy composition you need to make, and overall you can well get out of the polytime realm. So these two were the reasons we chose to get polynomially bounded interactions, but we haven't found yet any counterexample to the fact that concrete cryptographic protocols are polynomially bounded.
And maybe a final question from Slack. Is there another one? Right. Could you elaborate on how your developments provide an answer to your motivating question, namely whether one can define any crypto primitive in an equivalence preserving way?
Yes, indeed. I was looking at while preparing my talk, I was looking at at Slack, and I decided to kind of rearrange the result in such a way that this becomes more prominent. So point 3 here, down here, is precisely the answer of this question. If the input string is small, then second-order pseudo-random functions do exist, and then equivalence preserving authentication is indeed possible. Of course, there is a very high price to pay, namely that the authenticated function needs to be one which takes very short inputs. So logarithmic inputs of logarithmic length. Which is, of course, a very high price to pay. But if you just go from logarithmic to linear, well, you get to 0.2, and 0.2 is a negative result. So as far, this is the best we can get so far.
Okay. Yeah, thank you very much. So then proceed with the next paper. I think Pierre is presenting it. The paper is called Implicit Automata in Type Lambda Calculus, Aperiodicity in a Non-Commutative Logic.
Hi, can you hear me?
Yes. Hi, Pierre.
Super. I'll just share my screen. Oops. Okay. Okay. Can you see my screen? Super. So I'm going to reuse the slides of the video to give a short summary. Okay, so like in this paper, so in the title, you can see the two main ingredients of the paper, which is lambda calculus and automata. And essentially, this is part of a line of work where we try to study certain classes of functions in lambda calculus that corresponds to languages or transductions, and try to see if there are counterparts in automata theory. So for this paper, we're going to focus on a particular kind of simply typed lambda calculus, which is a non-commutative one, and the corresponding. And we're going to look at the class of languages defined in this lambda calculus, and it will turn out that this corresponds to star-free languages in the type. Okay, so essentially, so to give a bit of a background on regular languages, so regular languages are nice because we have several equivalent ways of describing them: regular expressions, automata, monoids, and like I said, like our main goal here with this line of work is to try to see if there is another characterization via simply typed lambda calculus. So our starting point here is a theorem of Filbron and Kanellakis that they proved in the 90s, which is that regular languages can be characterized as those languages that are definable in the simply typed lambda calculus. So the nice thing about this result is that it's not super obvious, in the sense that the notion of being definable in the lambda calculus just uses church encodings and does not refer to automata in any obvious way. Okay, so like I said, so for this work we're going to try to look at a restriction of this equivalence here, where here we are not going to use the full simply typed lambda calculus, and here we are not going to have all monoids, but only aperiodic monoids, and thus have a characterization of the class of star-free languages. Okay, so just to give you a rough idea about how things are defined in the simply typed lambda calculus, as I said, we're only using church encodings. So it means that we don't have a primitive string types. The type of string is actually derived from a simple type. So this O is actually a base type. Now, if we look, so yeah, that's what I was saying. There's no primitive data type. So now, if we look at the definition of star-free languages, or rather languages recognized by periodic monoids, we see that we need to forbid this kind of looping behavior in the monoid. And so this is something which is definable in simply typed lambda calculus. And one way of forbidding this kind of behavior is to restrict the order in which the argument can appear in a lambda term. So this leads us to our main result, which tells that a language is star-free if and only if this language can be defined via a lambda term in a non-commutative affine lambda calculus. So much like the case of the simply typed lambda calculus, we have a function from strings to booleans, where we allow to instantiate the base type of a string by some more complicated type. And here the restriction that we put is that A must be a purely affine type. That is, it does not allow for the nonlinear arrow. So maybe I can discuss very briefly the ingredients of the proof. So actually, this whole work just started by this observation that we have aperiodic monoids in the non-commutative lambda calculus. So this is something. This is a pure. So the soundness part of the result is just a property of lambda calculus, of non-commutative lambda calculus. And for the converse, we use the Cronroot theorem And to do so, we need to show that aperiodic sequential transducers are can be encoded in the non-commutative lambda calculus. And we do this using the Chrono theorem, which we think is interesting. And we also show that in our very restricted setting, where we have only linear type, if we relax just so slightly this non-commutativity restriction, we get back all regular languages, and thus we get back to the class of functions which are also expressible just in a simply typed lambda calculus. Okay, I think that's it for the summary, and I'll just leave you on this last slide, which tells that we're doing. So we're pursuing this work by studying transductions now, and I'll be happy to take questions.
Thank you very much.
Sorry.
Who would like to ask a question? Speak up, please.
I would like to ask a question.
Please.
Yeah, so I was wondering whether the kind of characterizations that you get stay there if you are not affine but just linear. So if say not even contraction but even weakening is not allowed, so can you still get your characterization?
Yeah, so that's an excellent question, and in fact, yes, we do have a similar result here. So it's a bit okay. So it's a bit technical here because so here do I have the definition of Boolean that we use here written on these slides? I think not. Okay, so there's a little complicated. We have a similar result for purely linear terms, but there is a little complication in the sense that the type of Boolean that we use in this work is O linear O. Which only works in the affine lambda calculus. It doesn't work as nice Booleans in the purely linear case. However, there is a more refined type of Boolean that can that I can just
Okay, so the more refined so the more refined form of Boolean that you need to use is probably the one by Terui. So A tensor A arrow A tensor A, something like this. So the kind of switching, two possible switching. I'm wondering.
Yeah, no, it's not that one. We're also considering a calculus with no tensor, just to keep things simple. I can spell that for you. So okay, just so that it's yeah, I don't know if there's multi-map in this. Yeah, okay, great. So this is the Booleans that we are using in the paper, right? Bloop. And the one that we're using there, so it's if I recall correctly, we do a thing where we take as input a function that takes two functions. So this is also a type of Boolean that was considered by some of the people. I think Noam Zeilberger considered that one.
So it's a second order type.
Yes, yes.
Thank you very much. It's fine. I don't want to.
Okay. Fine, but yeah, you can imagine the thing that you use this function, and on one place you feed it something, and the other the identity.
It's a way to simulate the tensor.
Yeah.
Thank you.
Are there further questions? I had the question whether instead of restricting your regular languages, you can also extend them and still keep the connection to lambda calculus. Is this conceivable or?
Okay, so for this whole line of work, we're only considering a subsystem of the simply typed lambda calculus.
Right, and then you would have.
Yeah, so this is a sort of upper bound. Now, I'm not saying that it cannot be done in a reasonable way otherwise, but for the simply typed case, yes,
Okay, yeah, so it will be tough to stay to my 8 minutes per paper, but we have to continue with the final paper of this session. The video presenter was done, Suchiu, And the title of the paper is Decision Problems in Information Theory. Dan is here. Very nice. Welcome.
Yes. Thank you. I hope you can hear me. Yes. So this is the title of the paper. So let me go directly to the slide where I want to present. So what we consider are constraints that are based on that are Boolean constraints over linear inequalities of information terms. So here is an example. So imagine that we have 3 random variables, x, y, and z, over finite domains. And H denotes the entropy of the joint random variables x and y. H of x, y, z denotes the entropy of the joint distribution of x, y, and z together. So this is an example of a linear inequality that holds between entropic terms for any random variables. This inequality holds. It's also a known inequality. The question is, how do we decide such inequalities in general? Given such an inequality, can we decide if this holds? So it has been conjectured until the mid-90s that all these inequalities can be derived from the basic Shannon inequalities, which are submodularity and monotonicity. In the late 90s, Zhang and Yong gave the first example of a linear inequality over 4 Boolean variables that is not a Shannon inequality. Later in the 2000s, Matus discovered that with 4 random variables, there are actually infinitely many inequivalent non-Shannon inequalities. So there is no hope that there is a finite number of inequalities that allow us to derive all of them. So we became interested in these because they have very interesting applications to database theory. More generally, you can consider, for example, taking the maximum of some terms, and then we can check that the maximum of these terms is greater than or equal to another term because it's a max inequality. We proved recently that these inequalities are equivalent to a problem in database theory, namely to the problem of checking containment of conjunctive queries under back semantics, which is another open problem. So you can further generalize it by taking conditional inequalities. So this states that if these inequalities hold on the left, then this inequality holds on the right as well. These have major applications to the implication problem of conditional independencies, which have been studied in graphical models and graphical probabilistic models for over 30 years. Again, the implication problem is it's not known to be decidable. And finally, you can generalize it to arbitrary constraints. So the question we asked was, since we don't know if any of these classes is decidable, and of course not even the simpler class, we don't know if it's decidable, can we at least place these problems in the arithmetic hierarchy? So let me just show you what the results are. Actually, it's the wrong page. So this is what we proved. If we start with the simplest ones, simple information inequalities or max information inequalities, it's very easy to see that the decision problem, given such an inequality, is it valid? This decision problem is in pi 1, at the first level of the arithmetic hierarchy. Why is that? Well, in order to refute it, you need to find a finite probability space with rational probabilities that invalidates that inequality. So you just check all these finite probability spaces until you find a counterexample or go forever. Now, when it comes to conditionals, however, this technique no longer works because a conditional might be satisfied by irrational probabilities, and you will never be able to get anywhere close to that conditional. So here, the techniques that we use here is a little bit more interesting. We proved this is the more interesting result. We proved that the conditional problem is in the third level of the arithmetic hierarchy. A final thought I want to bring up here is that you see here 2 columns. And this is an intriguing and a quite fascinating technical difficulties that you have to face when looking at these constraints. Namely, the fact that the vectors, the entropic vectors, the set of entropic vectors of a fixed number of variables is not a topologically closed space and is not a convex space. So what people are doing is they're taking the topological closure of this set, which also turns out to be convex. And there is a distinction of what you can say about these two kind of validities. This distinction doesn't matter for simple inequalities, but it does matter for the conditional inequalities. And I think this is all the time I have. I will stop here and take questions.
Thank you very much. Are there questions, please?
Yes, so I have a question. So I'm interested in the connection to the homomorphism and domination problem. And I was wondering if you know anything about if one fixes the right-hand side of structures. So in the database terminology, that would mean that we fix the class of databases satisfying some nice properties, but we don't restrict the queries.
No, I'm not aware of anything. I'm trying to think if I can say anything interesting. So if you refer to our result, that in that case we had to restrict the. No, sorry. If we're restricting the database, I know nothing about it. So it's an interesting question to pursue.
Thank you. Are there other questions? I learned from our tech support that we can go a little bit over time, but not too much, because subsequently there will be the social event. Yeah, so you can go to the social, and they will, because of that, they will kick us out, but maybe not immediately. So if there are no more questions to Dan, let's thank him again. And let's invite questions to all papers. Are there some questions that is to one of the papers that you still want to ask? Please go ahead. I have one more question to the paper about the monster, Hrushovski's monster CSPs. So this is some sort of negative result maybe, or but you also mention a potential positive result. You say the tractability, at least for finitely bounded homogeneous structures and their reducts, could be characterized by the existence of dissected weak NUs. That's what you say in the paper and also in the video, I think. Now, do you mean this globally, I guess? Yeah, globally, the existence of dissected weak NU polymorphisms.
Maybe, yeah. It could be the case, because in many examples we actually found them. So like in our linearization paper, if you remember, like all the known examples of tractable CSPs from known classifications have those terms. On the other hand, maybe somebody of my co-authors has a better explanation for this conjecture. I think
if not, I can make it more concrete. I
okay.
can make my question more concrete. So, so we have some nice sufficient conditions for polynomial time tractability that are quite general. So they should imply the existence of dissected weak NUs. For instance, if you have a canonical pseudo-Siggers polymorphism, can you prove in general that you have dissected weak NUs?
Well, if you have a canonical pseudo-Siggers, then that's in a finite algebra, right? Basically, I mean, this action types. So in this finite algebra, you'll have weak NUs and whatever, and therefore you're going to have
pseudo weak NUs.
Pseudo, yeah. Okay, so yeah, I don't know. It's a good question.
Some more questions about any of the papers?
But my guess is that, this is probably, yeah, it's a nice question, but it can probably be solved, but it's not an answer to the general, like if they actually characterize tractability, right? Okay. But yeah, that's.
But you meant it globally, yeah, not locally.
No, we meant in our paper we mean it locally, yeah.
Locally.
Yeah.
Local.
Yeah. Yeah.
You meant it locally.
Yeah. But it's true that in many cases we also get them globally.
All right. More questions? If not, we are hyper exact in time. It's 6:01. And yeah, please, everybody, go to the social room. And I thank you very much. I liked it a lot, the session. Thank you very much for contributing speakers. And see you around.